All right, hello there. So in this section, we are going to do arc length and curvature. So it's useful to be able to calculate the arc length of a curve. For one, this will tell you the distance traveled by an object when you're following the path of the curve, right? And so here's the formula for arc length. It looks horrible, but it's not really that bad. So notice that right here is your derivative of each item, the x part, the y part, the z part, or the parameter parts. And it's being squared and added together. So I hope this reminds you of the magnitude. So this is just the magnitude of the derivative. All right, and the integral of the magnitude of the derivative, right? So we can also write it like this, from a to b. You could do the square root, and instead of writing the derivative as f prime, you could put dx dt squared plus dy dt. The derivative with respect to t is your parameter there, and dz dt squared, and of course dt. And then what I said before is that this is like the simplified way of writing it. It is just the magnitude of the derivative. So notice that notation right here. The magnitude of the derivative, and there you go. All right. So let's try this example here. An eagle rises at a rate of 100 vertical feet per minute on a helical path given by this formula. All right, so the 100, we don't really, I mean, that's just part of the equation there. Like you can kind of see it right here, but they gave me the formula. All right. So r is measured in feet and t is measured in minutes. How far does it travel in 10 minutes? So we're looking for the arc length. So we're looking for when it's traveling this path after 10 minutes, how far has it really flown? All right, because you can't just go from the bottom to the top because you've traveled around that curve. All right, so my arc length is my integral of from 0 to 10. And I have to do the magnitude of the derivative. So square root the derivative. So let's do the derivative. So actually I should have done that first. R prime of t. The derivative of 250 cosine t would be negative 250 sine t. Okay. Derivative of 250 sine t. Oh, no, wait a minute. Derivative of cosine is negative. Yeah. Derivative, that's correct. So 250 cosine t. And derivative of 100t would be 100. Okay, all right, so we're going to square each of these items. So I have negative 250 sine t squared plus 250 cosine t squared plus 100 squared, right, dt. Okay, so I want you to notice something about this part. So whenever you get some nasty business like this, notice that it's going to clean up nicely usually. So if I work this out, I would, whatever the square of 250 was, so I'll just put 250 squared, because the negative would go away. Then I have sine squared. Then I have 250 squared again, and cosine squared right here. So notice I can take out a 250 squared, so 250 squared, and then inside here I would have sine squared plus cosine squared. Well, sine squared plus cosine squared is 1, so that's pretty nice. So 0 to 10, I have a square root of basically 250 squared times 100, or plus 100 squared. All right, so 250 squared plus 100 squared. Pretty convenient, huh? All right, so now we're just doing the integral of a constant, basically. So when I do that, 250 squared plus 100 squared is going to be 72,500. So I have basically the square root of 72,500, integral 0 to 10 of just 1 dt, or just dt. Now remember, whenever you're integrating there, basically what you're going to get is t, and then you're plugging in 0 to 10. So we should kind of know that all we really do is we just multiply our answer by the subtraction of 10 minus 0, right? So I have like 10 minus 0 times radical 72,500. Okay, so I have 10 radical 72,500. And I would go ahead and say that many feet, right? So you put that in your calculator. That is 2,692 2.6 feet traveled by that eagle in 10 minutes. All right, so a little over half a mile or something. All right, because a mile is what, 5,280 feet? All right, there we go. So sometimes when doing a problem, it's beneficial or necessary to change the parameters of the curve. So you're not going to see this that much because we're taking off parameterization, but I just wanted to show you that things that look very different could actually be very similar. All right, so for instance, these two curves below are really the same. We just might have to change the u values here, but so let's go ahead and see. You have t squared and t to the third. And so when I plug 1 into this guy right here, I would get 1, 1, 1. When I plug 2 into that problem, I would get 2, 4, and 8. Okay, so if I this next one is the same in a way, way it's e to the u, e to the 2u, e to the 3u, so it's something to the first power, to the second power, to the third power. So it's following the same parameters really, or the same path really, and let's just figure out what u should be. So I know that I need a number to start off with that when I evaluate that, I get the same as I got up here. So I need to know that e to the u should equal 1, because that's what it was doing up here, because I want to start in the same place. So what does u have to be to make that true? Oh, well, e to the 0 is 1. So this must be a 0 right here. And on the other side, I know that, let's do e to the u. I could use the others, but they're more complicated. I know that e to the u has to equal 8. So e to the u, oh no, I'm sorry, e to the u has to equal 2. We're doing the front one. Sorry. E to the u has to equal 2. All right, so let's go ahead and do the log of both sides. So ln of e to the u equals ln of 2. Maybe, because I'm trying to solve for u, so these cancel out. I get u equals ln 2. So this would have to be ln 2 right here. So if I wanted that to follow the same path with the reparameterization, I would need it to go from 0 to ln 2 to begin and end at the same place. But again, we don't really have to do that much because we're kind of skipping over the parameterization part. So these vector functions, this vector function describes the same curve but with different parameters. They are parameterizations of the curve C. So the arc length for each boundary is equal. So we basically figured out the boundaries so that the arc lengths would match. For vector functions, our convenient parameter is time with a t, right? When we are examining motion or a change in position over time. Okay. All right, so let's find the arc length of this one. And we want to do it from 1 to e. So that 1 to e tells me that those are my boundaries on my integral. Okay, and again, I need the magnitude of the derivative. So it's beneficial to just find the derivative real quick. So that way you can just use it. So derivative of t squared would be 2t. Derivative of 2t would be 2. Derivative of ln t would be 1 over t. Okay, all right, so I need the magnitude of the derivative. So my 2t would be squared, so I get 4t squared. Next in the middle, I would square the 2, so that's 4. And then I would square the 1 over t, so that's 1 over t squared. All right. So let's clean this up a little bit, because we can actually do this integral, but the way it looks now, you'd be like, oh, I don't know what to do. So let's try and fix this up a little bit, this stuff inside here. So let's get a common denominator, because if I can have the denominator be t squared, then I can do the square root of t squared and get rid of the denominator in some way. So let's get a common denominator, t squared. So that means that this 1 is going to stay. 4 is going to gain a t squared, and then I would need 4t to the 4th. Okay, so basically I multiplied the first two things by t squared, and then the 1 over t squared, it just stays at 1. All right, so that top part is factorable. So look at this top part. Let's split it up. This is perfect squares here. I got 2t squared and 2t squared to make my 4t squared, and then a 1 and a 1. So note if you check the outside and the inside, 2t squared times 1 is 2t squared, and then you get the same thing in the middle, so you add them together. That's how you get in your 4t squared. So these are both pluses over t squared. All right, so let's fix this up. So I'm going from 1 to e. I have a radical now of an expression that's a square. So I have 2t squared plus 1 squared over t squared. Okay, so let's go ahead and do my square root. So the square root knocks off the squares, so I get 2t squared plus 1 over t. And I'm doing my integral 1 to e and then dt. So a little bit of fixing up, a little bit of algebra there. All right, so why don't we go ahead and divide these things? Because still, like, why do the integral of you can't do the integral of a fraction like that. So let's divide these into two pieces. All right, 2t squared over t just becomes 2t, plus 1 over t is just 1 over t. And you should put some parentheses to kind of hold that together. Okie doke. So we know the integral of 1 over t is ln t, right? And we know the integral of 2t is 2t squared over 2. So that would be t squared plus ln t. And I have to evaluate this from 1 to e. So if I plug in e, I get e squared plus ln of e. Minus, when I plug in 1, I get 1 squared plus ln of 1. All right, well, ln of 1 is 0. Ln of e is 1, so I have e squared plus 1 minus 1, so I have e squared. And there we go. So easy when I do it, right? All right, so the next little part right here, so that part was arc length, and this last part is curvature. So when we're doing curvature, an important use of arc length is to find the curvature. So the measure of how sharply a curve bends. So the curvature is easiest to compute if it's in terms of the parameter t. All right. And so curvature is, like I said, let's say you have a curve, like this, oopsie, this curve right here. So if you were thinking about traveling along that path, all right, when I would travel along, let me get a highlighter. I'm sorry. All right, so let's say I'm traveling like right here. Like if I was driving a car traveling right there, it's not that curvy, right? Like it's kind of like a straight road. But as I get closer and closer to here, it gets curvier and curvier. So really curvy right there. And then over here, oopsie, not so curvy anymore. Not so curvy, but really, really curvy right here. And then not so curvy. So the curvature changes as it goes around your function, as it travels along the path. Okay? And so you'll see that in the next couple examples that we do also. All right, so here we go. So there's your formula for the curvature. You have your letter K. So this is kind of like a complicated little formula right here. So pretty much I'm not going to make you do it that way because it's like really tedious. I mean, you'd have to find the derivative of the tangent vector. All right, so you'd have to find the tangent vector and then do the derivative and then do the magnitude. All right, over the magnitude of the derivative there. And this up here, actually, it's not just a tangent vector. This is the unit tangent vector. So this would be like a kind of a tedious process. so it can also be used, you can also find the curvature this way. So this is the one we're going to use. Because see, this just involves r of t, r prime of t, just a bunch of derivatives. Okay, so we don't have to find like the unit tangent vector and all that kind of stuff and do the magnitude of it. That would be like a nightmare. Okay, so, but what we do want to do is this. So I'm given r of t in this example here. So right away, I want to find r prime of t and r double prime of t because I need them for my formula. It's easier if you just find them at the beginning. All right, so r prime of t. So t squared is my first thing, so it's going to be 2t. This guy, the derivative there would be 2t squared. And this last guy, the derivative is 2. Right? Then the second derivative, the derivative of this one would be 2, 4t, and 0 nicely. Okay, so there's two choices here. The first choice is to actually, they told you in this problem, we want the curvature when, whoopsie, oh God, give me a second. All right, I want the curvature when t equals 1. So kind of the easiest thing to do is like literally plug in 1 into these problems. So if I plug 1 in into r prime, I get 2 2, 2. If I plug 1 into r double prime, I get 2, 4, 0. Okay, and then I'm going to use these vectors and I'm going to like calculate this formula right here. Okay, so first of all, I need the cross product of these two things for my numerator. I need the magnitude of the cross product, in fact. So why don't we do the cross product right here? So let's do the cross product right there. That's a little squiggly bracket right there. I don't know what I was trying to draw. All right, so cross off the first column, and I would get, for the other four numbers, I'd get 0 minus 8. So it would be negative 8. Cross off the middle column, I would get 0 minus 4. So it's negative 4, but I changed the sign. And then cross off the last column, and I would use the four remaining numbers. I get 8 minus 4, so 4. So there's my cross product. Now I need the magnitude of the cross product. So k of 1 is, I need the magnitude of this thing right here. So square root 64 plus 16 plus 16. All right, and then on the bottom, I need the magnitude of the derivative, and I'm going to have to cube it. So the derivative, this guy right here, his magnitude is 2 squared, so 4 plus 4 plus 4, and we have to cube it. Okay? All right, so we're just going to clean this up. The top part comes out to the square root of 96. The bottom portion comes out to square root of 12 cubed. All right, and however you like to go about reducing that, I guess we'll reduce it a little bit. All right, when I got the square root of 12 cubed, so let's see, square root of 96. If I have square root of 12 3 times, 2 of them could cancel out and just become a 12, and then I'd have the square root of 12 still left over. So you follow that? Radical 12 times radical 12 times radical 12. A 12 pops out, and then I have radical 12 left over. All right, so that way my 96 does divide by 12, doesn't it? Let me see, 80, 70, 96 divided by 12. I think it's 8, right? 12 times 8, I should know this, right? 12 times 8, yeah, 16, carry 1, 96. All right, so 8. So this cancels out. This could be an 8. All right, so I have the square root of 8 over 12. And then 8 is 2 radical 2. So 2 radical 2 over 12. So I end up getting radical 2 over 6 to reduce that down. Now, frankly, I don't really care that much. I mean, I guess we could leave it like that, but, you know, you could do the other thing. All right, so the other way to do it is to leave it in its t format. So doing that would be a little bit more tedious, but let's go ahead and do it. So I'm going to do my cross product of my r prime of t. So that would be 2t squared, and 2. And then my second derivative is 2, 4t, and 0. So I'm doing my, oops, I don't need that comma. Okay, so I'm doing my cross product here. All right, so cross off the I column. So with other 4, we would get 0 minus 8t. So that's going to be a negative 8t. Cross off the center column. I'm going to get 0 minus 4, so negative 4, but change the sign. Cross off the k column, I would get 8t squared minus 4t squared, so that's 4t squared. Okay. All right, so let's make our formula. K of t, because I don't know, I'm not plugging in the 1 yet. I have to do the magnitude of the cross product. So the square root, 8t squared, I'm going to get 64t squared plus 16 plus 16t to the 4th. Okay, and then on the bottom, I have to do the magnitude of r prime of t to the 3rd power. So r prime is 2t, so it's going to get me 4t squared plus 4t to the 4th plus 4. And so at this point, you plug in 1 and you'll get the same answer that we would get over here and over here. All right, so you can keep it like symbolic and keep the t's in there. I think it would be easier if you know the number, just put the numbers into your derivatives and then you're working with numbers instead of all these expressions. Okay, so either way, same answer. All right, last page here, so curvature. So the ones we were just doing, this is when we were given an r of t. You were given a vector function, all right? So sometimes you can be given just a regular old problem, all right? This is just like a regular function, like y equals f of x. So here's our formula for the curvature then. So it's the magnitude of the second derivative, or the, hang on, so more like the absolute value of the second derivative, because we don't have a vector anymore, it's just the absolute value. And the bottom, 1 plus the first derivative squared to the 3/2 power. Okay, so let's take a look. So we're going to use it right here. Find the curvature of this parabola at these points. All right, so my f of x is x squared. My derivative is 2x, and my second derivative is 2. All right, so those are all the things I need for my formula. So my curvature. So my k equals, I take my absolute value of the second derivative. Well, the second derivative is 2, so I'm going to get a 2. All right, on the bottom, I have something to the 3/2. So I have 1 plus the first derivative squared. So 1 plus the first derivative was 2x, so if I square that, that'll be 4x squared. So this is my formula for the curvature. All right, now remember what a parabola looks like. All right, we got a parabola, 0, 0, it goes to 1, 1, it goes to 2, 4. This is just like the right side of a parabola, right? Okay, so, and we have our parabola that's coming up the other side as well. All right, so let's go ahead and plug in x equals 0. So at 0, that's my x. Here's my curvature. All right, so at 0, if I plug 0 into my curvature equation, I get 2 on top, and the bottom is 1 to the 3/2, so it's 2. At 1, if I plug 1 in there, I get 2 over 1 plus 4 on the bottom, so I get 2 over 5 to the 3/2, which comes out to 0.18. All right, and then if I plug in 2, I get 2 over 4 times 1 plus 4 times 4, so 17. So I get 2 and then 2 over 17 to the 3/2, which comes out to 0.03. So watch as I follow along here, or follow along as I go along here. So watch what's going on. So what's happening here, at 0, the curvature is 2. Because at 0, this graph is like super curvy. But at 1, it's not so curved because the curvature is lower. All right, and then finally at 2, right here, the curve is not curvy at all, so the curvature is very small, it's like 0.03. So the curvature is like the amount that it's curved at that moment, right? The level of curve. Okay, all right, and then this one, we're just going to go ahead and analyze this. I already have the picture for us and everything. So let me get my pen back, and we're almost done. Yay. All right. So use a graphing calculator or Desmos to graph both the curve and its curvature function. So let's find the curvature function. So for the curve, I got f of x equals x to the 4th minus 2x squared. F prime of x equals, oops, oh no, 4x to the 3rd minus 4x. And f double prime would be 12x squared minus 4, right? So put that into my curvature, and I have the absolute value of the second derivative of 12x to the 4th minus 4. And on the bottom, I have to the 3/2 power, and I have 1 plus the square of the first derivative. So 1 plus 4x to the 3rd minus 4x squared. All right, I'll rewrite it in a second. But anyway, so what I did is I put this guy in the problem in there, and over here, that is pictured in red. That is, a 4th power, it's a polynomial. And then the blue one is this one right here. So look at what's happening. All right, so the highlighter about green. Okay, so the red one, not too curvy right here. Right here, not so curvy. That's why the curvature is like very low, like almost no curve. But as the red one comes down here, it starts to get really curvy right here. That's why you see the curvature right here grow. The curvature is really high. Also, look here, curvature, super curvy on the red graph, super high curvature. All right, then the curvature gets lower because as you start to move over here, the graph is not curved anymore. Okay, so curvature is like a positive thing. Because it's just like an amount of, like a distance almost, but it's not a distance, it's amount of curviness. Okay, so anyway, I thought that graph was kind of cool. But all right, so next time in class we'll be doing this section, and I will see you then. Bye bye.